Hey everybody, today I just wanted to go over a couple of examples on the Unit 2 practice test just to kind of get you working. So I encourage you to work together with your classmates to try and see if you can't solve a lot of these problems. And I'd like you to have these done by next class. So let's go ahead and take a look at just a few random smattering ones. Let's take a look at the group 1 through 4, simplifying the following expressions with integer denominators. So that means we want no radicals in the denominator. So the more difficult ones tend to be ones where we have binomial or two-term expressions. So let's go ahead and take a look at number 3. Let's do number 3 together. Here, remember what we want to do is multiply by the conjugate, so that way we can start to cross some things out. Now the conjugate is just going to be the term with the radical needs to have an opposite sign. Okay, so we have 3 minus 5 square root of 2. I'm going to multiply both top and bottom by 3 plus 5 square root of 2. And resist the temptation, again, to cancel things out. And remember that we had a shortcut for our denominator when we multiplied out. We squared the first term, so 3 times 3 is 9. And then we square the second term. 5 times 5 is 25. And then multiply that by 2, because the square root of 2 squared is 2. So that's going to give me minus 50. Okay? Now, the numerator, we have to do a little bit of foiling. And when we FOIL, we have negative 3 times 3. That's going to give me negative 9. Negative 3 times square root of 2. Negative square root of 2. Now we multiply the plus 3 square root of 2. And then square root of 2 times 5 square root of 2. That's going to give us 5 times 2. And then we just want to try and simplify everything we can. Denominator is pretty easy. That's negative 41. Now we look for anything that are like terms. Well, like terms I have are negative 9, and then 5 times 2 is going to give me 10. So that's going to give me a positive 1. Okay? Then I look at the negative square root of 2 and the positive 3 square root of 2. You're going to add together the coefficients that are in front of the radicals. So that's going to give me negative 1 plus 3, and that's positive 2. The radical 2 stays there. So we now have 1 plus 2 square root of 2 over negative 41, but we don't put negatives in the denominator. So really you can just put the entire fraction with the negative, and it's going to be negative 1 plus 2 square root of 2 over 41. Or the other way that we could see that is put the negative to each term in the denominator. Since both of those are positive, then they both turn negative. And that's another way that we can look at it. So those two things are equivalent statements. Now, next we want to try simplifying each one of these expressions. Your answer should have only positive exponents. So this goes back to lesson 2.2. Okay, so let's go ahead and try one that's going to utilize a bunch of different things. Let's go ahead and take a look at number 9. Number 9 is a good one. The expression 4x squared y to the 4th divided by 2x to the 4 y to the negative 2 can be rewritten as a times yb, or y to the b over x to the c. Let's go ahead and try and do that. Well, a, those are my coefficients. That's the 4 and the 2. Well, what's 4 divided by 2? That's pretty straightforward. That's 2. Okay? So a is going to be 2. That's easy enough. Now let's go ahead and try to reduce these ones. We have x squared over x to the 4. That's the same thing as saying x times x over x times x times x times x. And we can see that I have x's canceling out here and here. And that's going to give me x, 2 x's in the denominator. Right? You can also use that rule that we are subtracting our exponents by dividing numbers with the same base. So 2 minus 4 gives me negative 2. Negative exponent goes in the denominator. Now we have y to the 4 over y to the negative 2. Well, what's going to happen with that is we can think about anything with negative exponents going to go to the top. And then that's going to be y to the 4 times y to the 2. But we know when we're multiplying two numbers with the same base, what's going to happen? We add together the exponents. So 4 plus 2 gives me 6. And now we have all over 2. So we have our a, our b, and our c. A equals 2. B equals 6. C is going to equal 2. The sum of all of those, 2 plus 6 plus 2. That's what we were ultimately asked to do. And that's going to give me 10. Okay? Let's go ahead now and jump down to our next section, something from section 2.3. Okay? Let's go ahead and take a look at Number 16 is going to be really pretty straightforward, but I want to make sure we understand it. So everything inside the radical we can think of as getting an exponent here. Both of these terms have an exponent of 1, so I can think about there being an exponent of 1 for the entire thing. Now, exponents inside of a radical can be, or outside of a radical, can be thought of as a rational exponent with an exponent in the numerator. Okay, so the 1, that's the exponent for the 2 and the x, is going to go in the numerator of my fraction. And then the index is going to be the one that is going to go in the denominator. Now, we have to be really careful about this. What's inside the radical? What's getting that denominator 4? Is it just x? Because that's how it's written right now. What do we want to do to make sure it's both the 2 and the x that get this 1 over 4 exponent? We need to put it in parentheses. This is our correct answer. Okay? Now, going the other direction, we can do something like that with, let's say, number 19. Simplifying x to the 1/3 times 2x squared to the 1/2. Okay, there's a lot going on here. X to the 1/3, there's nothing I can really do with that yet. Okay, but what I could do is I can maybe write that as a term in a radical. Okay, now I don't know if I want to do that yet, so I'm going to hold off for just a moment. Okay, and let's go ahead and take a look at the next one. So I'm going to leave this as x to the 1/3, but let's go ahead and apply the 2 getting the 1/2 exponent, and then we have, this should be a multiplication symbol in between these two, sorry, and then we have x squared to the 1/2 power. Well, x squared to the 1/2 power, power to a power rule says multiply them. That gives me 2 over 2. Okay? Now, putting all of this together, we can do this as x to the 1/3 times the square root of 2, 2 to the 1/2. We usually don't like to write rational exponents if we don't have to, okay, or unless we're explicitly told to. So in this case, I want to write this as a radical. And now the next term is times x to the 1, okay? So how do we work with this? Well, we have two numbers with the same base that we are multiplying. Doesn't matter the order of that multiplication. We know we're still multiplying x to the 1/3 and x to the 1. We are going to add those exponents together. So that's going to give me square root of 2 times x to the 1 over 3 plus, let's change that to 3 over 3, writing that with an equivalent fraction so that way we can add these together. And that's going to give me x to the 4 over 3. Okay? Now, still, it's a little bit weird to have one term as a radical and one term as a rational exponent. So let's write everything as radicals. And so we have square root of 2 times the index is going to be the denominator, 3, the third root of x to the 4th. Okay? So we can write it like that, and that's perfectly acceptable. Okay? Now, there's another way that might not be, that you might want to also write it. We can think about, hey, there is a factor of x cubed in here, and I could write that in a couple of different ways. So that could be x cubed times x to the 1, which really tells me that's the cube root of x to the x to the 3rd power. That's x, right? When my index matches an exponent inside the radical, we can pull that term out. And then I still have one lone x term inside here. So we could write this as square root of 2 times x times the cube root of x. So lots of different ways that we could write this. And again, what I want to do is just try and show you different options, because especially since the ACT is a multiple choice test, I want you to be aware of every single different way, or lots of different ways that you can express your answers here. Okay? For the purposes of our test coming up, you will be able to write it in one of the acceptable forms, and you'll find that on the multiple choice. Okay. Let's go ahead and move on to another question. Maybe we want to rewrite something in exponential form. So now we were looking at logarithms. And one of the things we want to try and now do is write this as a logarithmic expression or a logarithmic equation. Okay? Hopefully with this first one, number 20, we can do this one super quick. You might not remember, but hey, there's no base here. What do we know the base is supposed to be if it's not there? That's the common log, and that's base 10. When we don't write the base, we know that's base 10. So we'd say 10 to the y equals x. And now it's in exponential form. Same token, when we look at number 21, ln is log base e. That's what natural log tells me. So we have e to the n equals p. Both of those are ways that you can rewrite logarithmic expressions into exponential form. 22 does the same sort of thing, except it's actually giving you the exponential and you want to rewrite it as a logarithmic. So it's just going the other direction, okay? Now, when we look at these next couple of groupings, we are looking at trying to condense logarithms, okay? Condense or expand logarithms. And we want to try and rewrite them as one single logarithm oftentimes. That's helpful for us to be able to solve logarithmic equations later in the future, or even exponential equations sometimes too, doing the expansion or the condensing. Let's do number 25. 25 is a good one. Okay, so we have natural log of c plus the natural log of a over 3 plus natural log of b over 3. So I'm going to write this as ln of c plus 1/3 times the natural log of a. Okay, that's an equivalent expression to natural log of a over 3. Dividing by 3 is the same thing as multiplying by 1/3. Okay, I'm going to do the same thing here. Okay, and now what we want to do is try and rewrite this because we're all using the natural log. The base is the same. The base is e. Let's go and rewrite this all as one natural log. Okay, and we're going to put everything here in parentheses. Now, what are we supposed to do? Well, anytime we see the addition, that means we are multiplying items. Okay, before we do that, though, we have to remember one other thing. I neglected to mention this. Anything that's in front can go to the exponent. Anything that we are multiplying in front of a natural log goes to the exponent of the argument, of the term that's inside the logarithm. Okay, so we can think about that as the natural log of a to the 1/3 power, natural log of b to the 1/3 power. Okay, now let's go ahead and put everything together. So that's c times a to the 1/3 times b to the 1/3. And again, often we don't like to see those rational exponents, or we don't write them that way. So we can write this as natural log of c times the cube root of a times b. Notice there's no exponent for the a or the b. It's just 1, and then the index is the root that we are taking. That's the denominator there. Okay, so this is a pretty common way that we would see this kind of expression. You could end up seeing it as ln of c times a to the 1/3 times b to the 1/3. We could end up seeing it like this, c ab to the 1/3, indicating that both of those expressions are going to be getting the natural log. Either way is going to be considered acceptable. Now, let's go the other direction. We want to write as the sum or difference of these two. Okay? Now, what we can try to do is look at something that's a little bit more of an IB style question in number 32. 32 is a good one. Okay? So 32, let b equal log base 2 of a. Okay, where a is greater than 0. We want to write down the following in terms of b. Well, we're going to just kind of treat this very simply. I'm going to move the 3 into the front, because what I want to try and do is get terms to look like log base 2 of a, because I know what log base 2 of a equals. So this is 3 times log base 2 of a. Now, because of this equivalence here, I can replace, anytime I see log base 2 of a, I can replace it with b. And that's exactly what we are expected to do. So that's going to mean that's the same thing as 3b. Not 36, that's a b, 3b. We'll do the same thing with the next one, part b, log base 2 of 8a. Okay? Log base 2 of 8a, this is a little bit tougher for us to start to look at. Well, what we can do, though, is say, I can separate the product here, 8 times a, as two separate logarithms. This is the product rule of logarithms. If our argument contains a product, we can separate that out by a sum of two logarithms. And now this might not seem like all that great, but hey, look at that. We've got log base 2 of a. That's going to equal b. But what about log base 2 of 8? That's actually a number that we can evaluate. Remember, this is saying 2 to the what power equals 8. Well, 2 to the third power equals 8. So what does log base 2 of 8 equal? It equals 3. So this expression, log base 2 of 8a, in terms of b, can be rewritten as 3 plus b. Pretty slick. Okay? Now, from the last lesson that we looked at, solving exponential equations. And again, what we have is a few different ways that we can look at these equations. The first set of questions that you're looking at here are going to ask, can you get the bases the same? That's what you should recognize when you see two different numbers that look like they may share common factors, right? All of these are going to likely be able to be rewritten utilizing the same kind of base. So let's look at maybe number 36. 36 is a good looking one, okay? So 36, 216 times 6 to the negative 2k equals 6 to the negative 3k. You might not remember this, but I do know my powers of 6 for at least a few of them. And I know that 216 is 6 to the third power, okay? So I can rewrite this expression as 6 to the third power times 6 to the negative 2k equals 6 to the negative 3k. And we're almost there. What we want to do now is see this and recognize that, oh, there's that product rule. I can now add these exponents because of that product rule. Write it with the same base, but now the sum of the two exponents. 6 to the 3 minus 2k will equal now 6 to the negative 3k. And as we went through in our last lecture, you know that once the bases are the same, you can ignore the bases and just solve the equation that's made by the exponents. Okay, doing a little bit of simple algebra, we can say that 3 is going to equal negative k, and then that tells me that negative 3 will equal k. And I have solved for my variable, turning something really gross, an Algebra 2 style question, turning it into an Algebra 1 style question in just a few steps by knowing those properties. Okay? And that's what you want to try and do with each one of these. Know those properties, be able to turn it, something gross, into Algebra 1. Last question is that we can go over. Solving each of these equations, we want to utilize one of those log calculators for these types of questions, okay? Because with an exponential equation like this, if we can't get the same base, then I'm going to want to try and use a log calculator to do that, okay? Now, we can go and pick one. I'm just going to pick one at random. I'm going to say, let's go with number 40, okay? So let's go ahead and do number 40 together. Remember, our first step should be trying to get the base by itself, okay? Getting the base by itself means adding that 0.1 to both sides. So we have 7 to the negative 5n equals 55.1, okay? That's simple addition, right? Now, we can't divide by 7. That's a very common mistake. As soon as they, oh yeah, we just divide by 7 and then we're going to divide by negative 5 and boom, we're home. No, this is an exponential equation. We've got our variable in the exponent. So there's two different ways that we can approach this. We can take the log of the same base with both sides, or we can rewrite as a logarithm. Either way works. I'm kind of a fan of taking the log of both sides. It's just the way that I am. I don't know why. It's actually even writing more, but for some reason, this just kind of clicked with me when I was first starting to learn how to do this. I think because it was like, oh, algebra. Algebra means doing the same thing on both sides. I get that. I understand it. Then I remember that taking the log of the same base, these, you can think about them as canceling out, and we are left with just the exponent as the expression. And again, I know the log base 7 at 55.1, that's a number. That's something I could punch into my calculator right away, but I'm not going to yet because my n isn't satisfied yet, or it's not isolated yet. And what I like to do is try and make sure that I have isolated everything. I've done all my other algebraic operations. I only want to touch my calculator one time. That's it. Okay? So we're going to divide both sides by negative 5. And this could be considered an answer. Negative log base 7 of 55.1 all over 5. That would be a perfectly acceptable answer in a lot of different worlds. But if we are going to punch this into a calculator, we can do that. So if I'm going to take log base 7 of 55.1, you guys get to sit awkwardly while I try and find my log calculator, punch it in. This is going to give me negative, or I'm sorry, not negative, it's going to give me negative 2.0602 ... so on and so forth, and then dividing by 5. And then when we take that value and we divide it by 5, we end up with 0.412, and that's a negative value. And negative 0.412 is indeed 3 significant figures, or 3 decimal places. That is our solution for n. And there you have it. All right, I hope you guys found this at least somewhat helpful to get you started. I will be happy to go over any other questions you guys have when we are in class together again. Thanks so much for watching. Have a great day.